First, like I mentioned, we'll be covering stoichiometry, which should be reviewed, but we'll go over it quickly. So the first step to any chemical reaction is you have to make sure that chemical reaction is balanced, right? What does balanced mean? Well, a balanced reaction is a reaction that has the same number of molecules on the left side of this arrow and on the right side, right? So if you look at these two, this reaction, these two sides, they're obviously not balanced because you notice there's 6 carbons on this side and only 1 carbon on this side, right? You know, you can't create or destroy matter, so those carbons had to end up somewhere, right? So they couldn't have just disappeared as this reaction is progressing. So what this means is that you actually have to balance it by making it like this, right? You have to multiply this whole CO2 by 6 to make 6 carbons, right? Now you have 6 carbons on the left, 6 carbons on the right. The carbons are balanced. And then we look at the next molecule, which is H, 12 H's on the left, only 2 on the right. Again, we have to do the same thing. 12 H's on the left, 12 H's on the right. Then we look at oxygen. We have 6 here, 2 here, that's 8. Whereas we have 12 here, 6 here, that's 18, right? So what we can do is just do this, right? Now we have 12 plus 6, 18 on the left, 18 on the right. Essentially, all we're really trying to do is just making sure all of the molecules that are on the left are in the right, right? Because we don't want anything to get created or destroyed. Okay, so that's how balancing works as the basic idea, right? And this is just showing what I wrote before, right? This is the balanced equation of a very common reaction that you'll see: glucose plus oxygen to carbon dioxide and water. The burning of glucose to get, and you see ATP energy on the right side as well. That's very basic principle of how our bodies make energy, right? You burn glucose. But the goal here is number of atoms of each element must be equal on both sides, right? Next, we want to talk about oxidation number, which is also fairly simple. Oxidation number refers to the charge on each molecule in a compound. So for example, this compound, Fe2O3, has 2 different molecules, as an Fe and an O, right? 2 different components that make it up. The way we usually do this is there are some common oxidation numbers, which is elements that always have the same charge, no matter which compound they're in. So some common examples are column 1 elements in the periodic table, like sodium, potassium, etc., cesium, anything like that. Column 2 elements like magnesium, calcium, those are usually +2. Whereas column 1 is +1. I'm not sure if I mentioned that. +1. Column 2 is +2. Oxygen is pretty much always -2, except when it's bound to fluorine, but you won't really see that in the MCAT. That's a very, very rare situation. And usually halogens like chlorine, fluorine are -1, right? So if we know the overall charge of a compound, so for example, let's say this had an overall charge of 0, and if they don't give you a charge, that means it's usually charge 0, right? So they give you the overall charge is 0. You know that each oxygen has a charge of -2. This has -6, right? The charge of all of the oxygens in this compound are -6. But you know that this compound overall is 0. So what they may ask you to do is just find what the oxidation number of iron, Fe, is in this case. And the oxidation number of iron and a lot of the transition metals in particular, they, unlike these common oxidation numbers, they vary from compound to compound. So in this case, iron, since there's 2 irons, it has to make -6. Each iron, together iron has to be 6+. So that means between the 2 irons, each iron is 3+, right? And this is called Fe3. And it's written like this, just a Roman numeral 3. Right, and you may also see Fe4. So commonly you'll also see Fe4, which is iron with 4+ with an oxidation number of 4, right? like I mentioned, a lot of the transition metals have various oxidation states they could take depending on which compound they are in, right? And it's usually those that you'll be actually looking for rather than something like oxygen, which you already know the answer to before you even look at the problem. Okay, highly recommend remembering these common oxidation numbers. They're not very hard because the column 1 is +1, column 2 is +2. Halogens are the last column other than the noble gases. They're the second to last column actually, -1. Oxygen is one column before that and it's -2. And actually here's the periodic table. So these guys are all +1. These guys are all +2 usually. These are -1. I don't want to say that these are usually -2. Oxygen is -2, but sulfur is not always anything. So just remember oxygen. Actually, like for example, in this case, right? Like I mentioned, sodium, you know, commonly is +1. 2 sodiums, that's a +2. Oxygen, -2. There's 4, so that's -8. Assuming this is overall neutral, you have a -8 and a +2. How do you get from that makes a -6? How do you get from -6 to neutral? Well, this sulfur actually has to be +6, right? And that's very simple. Sulfur's +6. And it makes sense if you guys remember valence electrons. You want to either have a full or an empty shell, right? You don't want to have a half-filled valence shell. Valence shells usually have 8 electrons. So something like oxygen can be -2 to fill it up and become a noble gas, right? Sulfur can also become a noble gas-like by filling up its shell and becoming -2. It can become like argon, or it can just lose 6 and become like neon. Okay, it's just something you may remember. I know I went through that very fast, but I hope it was mostly a review for you guys. If nothing else, then I'll move on. Next, we want to cover equilibrium, right? So equilibrium, first, what is equilibrium? So equilibrium means that a chemical reaction is perfectly balanced, but not in the way that I was just talking about with balancing the equation in terms of number of molecules, but rather it's in a state where the reactants and products are in a balanced state as, I guess, if you want to think about it as the world sees fit, right? And that can depend on many, many different factors, right? It's a little bit hard to explain in words, and I'm sure you'll see what I mean. So essentially what it means is that the forward and the reverse reactions are happening at the same rate, and there's actually no overall change over time. Again, an important note, this does not mean that the concentration of products and reactants is the same, only that there is no change in time. So for example, if we want to go back to one of our older reactions like this, when this reaction is at equilibrium, it does not mean that there's an equal number of glucose and oxygen and an equal number of CO2 and H2O. What it does mean is that the amount of glucose and O2 that's being converted into CO2 is the same as the amount of CO2 and H2O that's actually being converted back into glucose, right? Any chemical reaction is not just a one-way trip. It's always a back and forth. Usually when you have something like this, where it just shows an arrow in one direction, it just means that the vast, vast majority of the reactions happening are in this direction, and only a tiny, tiny, tiny fraction are happening in the reverse direction. In equilibrium, it means there's an equal amount happening one way and the other way. Okay, so let's look at an example. So for example, here, N2O4 turning into 2NO2, right? And it has the double arrows, which signifies it's at equilibrium. So the reaction is happening in both directions at all times, right? Even at the very start, when you just put in N2O4 into an empty container that has nothing in it, the N2O4 will be converted to 2NO2 at a very fast rate. But as soon as it's converted into 2NO2, some of that 2NO2 will start getting converted back into N2O4, right? Just at a much lower rate. until you reach equilibrium, in which case they will happen at the same rate. So I can actually show you this graph right here. So this graph measures the concentration over time. So again, you start off just by introducing N2O4 with nothing else in a container like a jar. There's 0 concentration of NO2 at the start, and then rapidly it gets converted, right? And when it gets converted, it gets used up and more NO2 is made. And then it keeps going, keeps going, keeps going. So you reach this line. Okay. Please, everybody, if you could mute your mics. Thank you. So you reach this equilibrium point, and now you notice that the concentrations are over time. The y over x is no longer changing for either of these. So what that means is that N2O4 is still being converted. So in this case, it's clear to see N2O4 is being converted into NO2. It's very easy to see because its concentration is going down and NO2's concentration is going up. But in this case, N2O4 is still being converted to NO2, right? Even in this equilibrium region. But what's happening is that the same amount of 2NO2 is being converted back into N2O4, right? And because you're converting at the same rate, the overall amount actually doesn't change, right? There's still stuff happening, you just can't see it, right? It's like saying I walked 10 steps forward and then 10 steps backward. I essentially didn't move, but I was still walking, right? So you may not see that the displacement changed, but I was still moving. And even in this non-equilibrium section, right? Even in this non-equilibrium section, like I mentioned, it's very clear that N2O4 is being converted into NO2, right? We can see that by this trend. But at the same time, at all of these points, NO2 is being converted into N2O4 in the reverse direction. It's just happening much slower. And so the overall trend is that N2O4 is being converted to NO2, right? Even though the reaction is happening in both directions. So that would, like going back to my example, that would mean something like I walked 10 steps forward and then 2 steps backward. I'm still walking backwards a little bit, but overall I'm still moving forward up until this equilibrium region. And notice again, like I mentioned before, the concentration of each of these at equilibrium is not the same. They're very different concentrations. It just so happens that one is higher than the other. They could be equal, one could be higher, one could be lower. It doesn't matter. The concentrations don't have to be equal. All that has to happen is that the concentration over time, the change over time, is constant. It doesn't change. Okay, so there is this value called the equilibrium constant, right? Each equilibrium reaction has its own constant, which we write as KEQ, right? That determines whether the reaction favors the product or the reactants. Like I mentioned, once equilibrium is achieved, the concentration of products and reactants is not the same, at least usually it's not, or sometimes it's not. It could vary. But when we say one reaction or one side is favored, what that means is once it reaches equilibrium, that side will have a higher concentration. So if we see here, NO2 has a higher concentration at equilibrium than N2O4. What that means is this reaction is favored, right, going this way, and the product and NO2 is favored over the reactant. And that's evidenced by there being more of it at equilibrium than N2O4. So if the reactant was favored, this reaction would be favored going backwards to the reactant. And the concentration of N2O4 at equilibrium in this region would be higher than it is for NO2, right? That's what reactant favored would mean. But that's not the case here. Okay. And that's determined by the equilibrium constant. So equilibrium constants can range from being ridiculously small numbers like 10 to the negative 15th to ridiculously high numbers like 10 to the 15, or even higher or lower than those two. The larger the equilibrium constant is, the more it favors the reaction to the right, or the product. The smaller the equilibrium constant is, the more it favors the reaction to the left. So, for example, if we had an equilibrium constant like 10 to the 15th, right, that's a really, really big number, meaning that it favors the product very, very heavily. And at equilibrium, there will be much, much, much more product than there is reactant, right? You'll reach equilibrium, but at equilibrium, there will be much, much more product than there is reactant. On the other hand, a very small number, like 10 to the negative 15th, would mean that at equilibrium, there is much higher amounts of reactant than there is product, and this reaction is favored to the left, right, back towards the reactant side. And the actual equation for this reflects that. The equation for KEQ is KF over KR, which you don't really have to know. We'll talk about those later. Those are the rates of the actual reaction, but it can also be equal to the concentrations, right? Concentration of NO2 over the concentration of N2O4 at equilibrium, right? KQ equals concentration of product over reactant at equilibrium. And notice how the product is squared. That is because it has a coefficient of 2. So if any element has a coefficient, that coefficient will become its exponent, right? So if, for example, we had 3N2O4 going into 6NO2, this would be 6 to the 6th power, and this would be to the 3rd power, for example, right? Okay, so based on what I just mentioned, let's see if you guys can answer this question. I'm going to open the poll. Okay. So the majority of people voted for A, with C being with C and B also being other answer choices people have picked. So the correct answer actually is C. And let's go over why, right? So like I mentioned, KEQ equals, sorry, this is Q, equals concentration of products, which P, over concentration of reactants, right? And we know that for reaction 1, or reaction 1, the concentration of, I'm gonna ignore the coefficients for now. I'll like pretend I'm using the coefficients, but yeah, it's just annoying to write. And this is a little bit hard on this, but it would be C over D is equal to A times B, right? And they would have the proper exponents. So A would have 3, B would have 2, C would have 3, D would have 4, right? And you know that this C times D over A times B is equal to 0.1, or 1 over 10. I think that might make it easier to see. So you know that C times D over A times B is 1 over 10. They told you that. Now we want to see what it is for reaction 2. Well, we know KEQ of reaction 2 is equal to, again, products over reactants, except this time the products are A and B, and the reactants are D, C. Again, all with the proper exponents corresponding to the coefficients. I'm just not writing that out right now, but yeah. So KQ is this, right? So we know what C times D over A times B is. It's 1 over 10. So if you just did A times B over D times C, what would that be? Well, you know, of this, you can say C times D is equal to 1, and A times B is equal to 10, which we know because C times D over A to B is 1 to 10. Well, we know that A times B over C times D is 10 over 1, right? It's the inverse. 10 over 1 or 10, which gives you the answer of C, right? Does that make sense to everybody? Is it clear why it's not A, right? Even though it is the same, reaction in a sense, it's inverted, right? What was the products have now become the reactants. What were the reactants have now become the products. And essentially, how you can do this, what you can do with this is, so in this case, they gave you both of these reactions, right? But technically, if you look at it, this is the forward reaction. So I'm going to cross this out. This is this reaction, whereas this is like this, whereas this reaction 2 is this same reaction as reaction 1, except it's now this reaction, the backwards, right? This is reaction 2 now. It's the same thing, right? So you know that if the KQ for for one reaction is one thing, if you then kind of flip it, it's like the opposite thing, if you want to put it that way, right? If you flip it, it's the opposite for any equilibrium constant. Next, we'll talk about Le Chatelier's principle, right? Le Chatelier's principle states that equilibriums shift in response to external conditions. So, for example, if more molecules are put in, the equilibrium will shift in opposite directions to balance out. Like I mentioned, an equilibrium is kind of like a balancing, an equation or reaction that is completely balanced. If you put something in, it'll disrupt the balance completely. If you disrupt the balance, nature will try and find a way to kind of work around it and rebalance it a different way, right? One way that you can disrupt the balance is if you put more of something in, right? For example, like I mentioned earlier, right? This is like a graph like this, but if you put in more NO2 or more, if you put in more of the product or more of the reactant, the equilibrium will shift to try and compensate that, right? Because, of course, if you put in more of something, so for example, going back to this graph, if I suddenly put in more NO2, so now the graph looks like this, it's no longer balanced because the balance in NO2 has been disrupted. It needs to kind of find a way to rebalance itself, right? And because this graph would be messed up, equilibrium will be destroyed. It needs to find a way to rebalance itself. The way it does that is by shifting the equilibrium constant and the direction the equilibrium goes, right? Oh, sorry, went actually far. All right. Like I mentioned, you have NO2, and what was it, N2O4, right? If you're going this way, this is an equilibrium. If you add in more N2O4, you'll have more reactant. That'll break the equilibrium. It'll shift it to compensate. The reaction will automatically take some of the N2O4 you added, and it'll turn it into NO2, right? And that will actually like break the equilibrium, right? At equilibrium, the concentration levels over time don't change, where if you add in more N2O4, it will change. You'll have more NO2, right? More NO2 being produced, right? It'll speed up, essentially, if you want to think that way. Yeah, exactly. The increase in concentration will increase the rate, right? So, okay. And if you want to think of it mathematically, and I can actually show you exactly this mathematically, right? So KQ doesn't change, by the way. KEQ always stays the same for the same reaction, right? Doesn't matter how much N2O4 there is, doesn't matter how much N2NO2 there is. KEQ is the same for this reaction. Well, what happened is, so if, say you had a number. I'm just going to use numbers just because it might be easier to explain. Say the concentration of NO2 is 5. Concentration of N2O4 is at equilibrium is, say, I don't know, 10. So maybe actually it should be lower, but just pretend we're doing this, right? It doesn't really matter which equation we use. That means KEQ will be 25 over 10, or essentially 2.5, right? That's what KEQ is. KEQ for this reaction will always be 2.5, right? Well, what would happen if we took this 5, suddenly we added in a bunch more NO2 into the reaction? We added in so much that the concentration shifted from 5 to 15. Well, now 15 squared over 10 is no longer 2.5. Essentially, what that would mean would be that KEQ would shift. But we know that KEQ doesn't change, right, if you add in more. So we have to find a way to make sure that KEQ doesn't change, right? And we have to accommodate this 15 somehow. What the reaction would naturally do is it would take some of that 15, turn it into maybe 10, right? So take some of that away and turn it into some of this product, and some of this reactant, I should say, right? It will shift the equilibrium so that more reactant is being produced, right? And it may shift it to, I'm not actually sure how to make it'll be 100 on the top. Then to get 2.5, you would need 40, right? So take some of that and then convert it into 40 right here, right? That would give you 100 over 40, which is still 2.5, right? And the KEQ would remain unchanged. So it would take, so you put enough to make it 15, it would then realize, well, this doesn't work anymore. Take some away from that 15, give it to the other side to make the denominator bigger and itself smaller, to the point where KQ is again 2.5. That's just an example, right? Does that make sense? I guess was the old question. Okay. Another thing I wanted to point out is that equilibrium can be written in concentration, or it can be written as partial pressure for gases, right? So Le Chatelier's principle can apply to changing pressure as well as concentration. I'll give you an example. Here, we did KEQ is equal to concentration of NO2 to N2O4. KEQ also equals partial pressure of NO2, assuming these are all gases, which in this case they are, squared over partial pressure of N2O4. And I mentioned partial pressure in our recent lecture on fluids, right? So if we're talking about gases, we can still find the KEQ using partial pressure, right? Doesn't just have to be concentration. It can also be mole fractions, but that's I don't really want to get into that because you'll never really see it. But partial pressures you might see with gases. That's equally valid way to find KEQ. If you find it this way or that way, you should get the same thing, right? It should translate the same, right? And you can use partial pressures of gases. What that also means is that just like if you change the concentration in an equilibrium, it would cause a shift in the opposite direction. If you change the pressure, one of the gases, it would cause a shift in the other direction as well, right? If you change say the partial pressure of NO2, it would cause a shift. Generally, the best way to create a shift in partial pressure is actually by changing the concentration of the gas. But that's not the only way. You can also change it through temperature and total pressure as well. So you can change it by total pressure as well. Right, and yeah, Chris mentioned in the chat, you can change it through temperature or through partial pressure. And there are different ways that this happens, right? Right. I think that I can't really cover every single thing in detail because like people spend entire semesters college learning about kinetics, equilibrium, thermodynamics, all that stuff. Can't really spend that much time on it, but I'm trying to give you guys the foundation of the Chateliers Principle and the general equation for equilibrium constant so that you can then learn any other specific tiny things that you would need on your own. So for example, how does temperature affect? Well, or how does pressure affect? Well, knowing that the Chateliers Principle applies to pressure or temperature or anything like that, you can then figure that out, right? Just by manipulating the equation, right? And I would highly recommend trying to get used to that, right? Using information that you already know, because the MCAT will very often ask you to do that. Take information that you already know and then apply it to something that you're not very familiar with, but that is easily acquired from knowledge that you know, right? Yeah, KEQ is KQ. I didn't say it does change on temp. It changes. It's the same for any one reaction at any one temperature. That's what I should have said. Sorry, I apologize about that. Yeah, it's the yeah. Yeah. Okay. So next poll question, I'll relaunch the polling. Okay, so please take some time. Okay, closing the poll. So the majority of people picked answer choice A, which I'm happy to say is correct, right? So the majority of you did seem to get it. I'm gonna go over why, right? So again, I mentioned that with gases, one of the things that can affect equilibrium is the pressure, right? Well, so what we're trying to do is we're trying to change the pressure. First step is I think we should write out the equation, right? So KQ, and that's how we would know increase the formation of product is by increasing KQ, right? I mentioned that earlier. So KQ equals the partial pressure of the product, which is FeI3, over partial pressure of FeI times the partial pressure of I2. Well, you know that the partial pressure of anything that's not a gas is really kind of irrelevant, right? This and this, like aqueous solutions like these two, they aren't really impacted by they don't really contribute to the partial pressure. Essentially, all of the partial pressure in the solution is all I2. The aqueous solutions contribute so little to partial pressure that it's essentially non-existent. So increasing pressure would be essentially the same as adding in more I2, right? It would have the same effect as if you just straight up added more concentration of I2, right? So decreasing the pressure, obviously not. We need to increase the pressure, right? Because by increasing the total pressure, if you remember from my lecture on fluids where I talked about gases, increasing the pressure would obviously increase the partial pressure of I2, right? You increase the pressure of the partial pressure of I2, it's the same as increasing the concentration of I2, and it would shift the equilibrium to the right, by making more product be formed. So it's not B. Decreasing the volume while maintaining constant pressure. Well, if it's constant pressure, it's not doing anything. Doesn't matter about volume, right? But we know that in a container, in a set container, volume, pressure are inversely proportional. If you increase the volume without doing something that, like for example, in D, where you maintain constant pressure without doing some kind of extra work to keep the pressure constant, increasing the volume will decrease the pressure, right? Whereas decreasing the volume will increase the pressure. Therefore, we want to increase the pressure by decreasing the volume. Does that make sense? So, and just to reiterate, the reason that increasing the pressure won't have any effect on FEI3 or FEI is actually because partial pressure is only really for gases. Technically, liquids, solids, aqueous solutions do have a partial pressure, but it's like comparing 1 to a billion. If you add 1 to a billion, it's essentially just a billion because it's like a rounding error, right? It doesn't actually change. It doesn't really change the number, right? So essentially, liquids, liquids, solids, and aqueous solutions don't contribute to partial pressure. Only I2 or only gases do. So increasing the pressure would have no effect on this, no effect on this. All it would do would increase this, right? If you had something like, say, O2 or 2O2 here on the right, for example, if I was to add something to this equation, right, and pretend like this is balanced. I know it's not, but pretend. Now you have 2 moles of gases in the products and 1 mole of gases in the reactants. Now, when you would increase pressure as a whole, you would have the partial pressure of O2 would increase, PO2 would double, and PI2 would double as well, right? But because this has a 2 in front of it, right, 2O2, it would actually be squared. So it would be doubled squared, which is quadrupled, compared to I2, which is only doubled, right? So that would essentially give higher partial pressure or partial pressure equivalence to O2, making the equilibrium shift to the left. But that's in a different problem.